me just put it in presentation mode. Hello, everyone.
Iris, wait a little, please. Sorry, I was thinking that I was answering to Miguel. Just let me make some presentation, okay? Let it be as it is your presentation. Let it be, yeah. But I will make a short presentation and then I will introduce you, okay?
Sorry.
This is already on live?
Yes, Professor, yes.
Okay, so good morning to everybody. I first would like to send my compliments on behalf of the Director of the University of Porto. My name is Rui Faria and I'm the President of this jury. They will be discussing the thesis presented by Anis, who will present on the beginning of this discussion his work. I would like to send a compliment to all my members, my colleagues, members of the jury, but also the audience, relatives and friends of Anis probably, and colleagues, etc. So first of all, I would like to send a special acknowledgement to Professor Carlos Rebelo from the University of Coimbra, who will be the first advisor that will make the intervention. I would like also to acknowledge Professor Nicolas Antuzzi from the University of Bologna, Italy. We'll continue the discussion after Professor Carlos. It's a pleasure to have you here. And then we move to Professor Abílio Jesus from the field, who will also make the third intervention. And finally, of course, Dr. José Antonio Correia, who is the leader of the supervising team. I send him as well my compliments. So my last word is to Anis Mohabeddine. I would like to send you my best wishes that this day will be a good event for your memory, and also I think that we should have here a interesting discussion of your work. So as you have already appointed, you have more or less 30 minutes, okay? And then we'll have, after your intervention, we will have up to 2 hours of discussion. So we can start. So I invite you, Anis, to start your presentation, okay?
Okay.
And I also ask my colleagues to unmute the microphones just to avoid any feedback. Okay.
Hello, everyone. I am Anis Issam Mohabeddine, PhD candidate at the Faculty of Engineering, University of Porto. My PhD supervisors are Dr. José Correia and Dr. José Miguel Castro. And today I'm going to talk about enhanced fatigue and seismic performance of metallic structures retrofitted with CFRP. A large portion of existing metallic infrastructures are more than 50 years old. They were designed using conventional methods and materials which are not complying with the current standards. Additionally, they are subjected to increasing loading demands and frequencies. And some of them are suffering from aging problems such as corrosion and fatigue, and also severe damage in extreme events. The replacement of aging metallic structures is not feasible due to economic and environmental reasons. And some of them are historical, beautiful landmarks that belongs to the heritage of the city or the country. Therefore, the preservation of their structural integrity and their resilience after extreme events are of paramount importance. Carbon fiber reinforced polymers, CFRP, are widely used for concrete structures. However, when it comes to steel or metallic structures in general, despite some successful case studies that I'm showing here, very limited applications can be found worldwide. Bonded CFRP is a technology with a great potential for retrofitting civil engineering structures because they are lightweight, easy to transport, have a high strength, high stiffness, easy to install in practice, and do not alter the mechanical properties of the original structure and can preserve the architectural aspects. So some of my first questions during this PhD were why CFRP is not applied in repairing metallic structures and how to adopt or improve it to be applied in practice. So the aims of this research are first to understand the behavior of adhesive CFRP steel joints, then develop retrofit solutions and derive simplified design methods for metallic structural components subjected to service cyclic loading, which is fatigue, and extreme cyclic loading for seismic applications. The thesis is divided in three parts. First part is the characterization of adhesively bonded CFRP steel joints. And the second one is the application of CFRP to repair metallic components subjected to fatigue. And the third part is the application of CFRP for seismic design of steel structures. Let's start with the characterization of adhesively bonded CFRP steel joints. Limited research on CFRP steel joints can be found in the literature. Most of them were an adaptation of works done on CFRP concrete joints, made by the same researchers using the same materials, type of specimens, and models. However, the behavior between CFRP concrete and CFRP steel joint is fundamentally different. The adhesives available in the market used in the construction industry are tougher than concrete. Therefore, the damage will always initiate in the concrete, whereas in steel, usually the damage starts in the adhesive or in the CFRP, which is totally different. So we launched a large experimental campaign where I tested more than 50 double strap joints specimens, DSJ, that you can see here. And the influence of several variants such as the adhesive type, adhesive thickness, CFRP type, CFRP length, steel thickness, and surface treatment were investigated. The digital image correlation DIC was used to measure the strains on the back face of the CFRP. Here you can see some DIC results where I'm showing you some strain control plots in the vertical direction, where you can see here at the back face for different specimens with different adhesives. And you can see clearly that the specimens with ductile adhesives used in the automotive industry achieve very high strains compared to the rigid ones that we can find in the construction industry. And when we look at the force displacement curves, the specimens with ductile adhesives achieved very high strength, and also some of them developed some ductile behavior. And this ductile behavior is mainly occurring in the steel parts away from the joint. And this was confirmed using numerical analysis in Abacus, where we can see clearly that the ductility is occurring in the steel. Ductile behavior in the steel away from the joint means that the adhesive joint was stronger than the yield strength of the parent steel. This is a very promising result, because if adhesively bonded joints can be designed to be stronger than the parent material, this technology becomes more reliable and design procedures can be simplified significantly. Experimental results on joint strength. We can see that the ductile adhesives used in the automotive industry achieved higher strength than the rigid ones. Therefore, it can be concluded that they are more suitable for steel structures. However, in the construction industry, large amount of adhesive and CFRP are required due to the size of the members. And usually ductile adhesives are much more expensive than the rigid ones. So this will question the feasibility of applying these adhesives in practice. So I proposed a cost-effective biadhesive joint where we can use little amount of ductile adhesive in high stress concentration zones. And here you can see some results where I compare the specimens with rigid, ductile, and biadhesive. And you can see clearly that the specimens with biadhesive achieved very high strains, which are quite comparable to the specimens with ductile adhesive. And this can be also seen at the joint strength level, where biadhesive joint achieved very high strength, which is comparable to the ductile ones. And we can confirm that from numerical analysis, where we can see the stress concentration in biadhesive joint was reduced significantly compared to the rigid ones. And this we can see it in the peeling stress and in the shear stress. Now let's move to the application of CFRP to extend the fatigue life of metallic structural details. These can be divided in two subparts: fatigue strengthening using CFRP for non-cracked details, and fatigue repair using CFRP for cracked details. Let's start with the fatigue strengthening using CFRP for non-cracked details. I collected experimental data on open hole specimens from the literature with and without CFRP, as you can see here. And then I conducted a statistical assessment on the data and proposed PSN curves for specimens with and without CFRP. But what was important, I found important findings like during this work is that the fatigue life extension ratio due to the application of CFRP reduces as the stress range increases. As you can see it here clearly, the ratio is decreasing as the stress increases. This is mainly due to the influence of fatigue loading on the CFRP. So I proposed a new approach to predict the fatigue life of CFRP retrofitted details, considering the influence of fatigue loading on the CFRP patch using a residual stiffness model that was validated with experimental data. So the actual stresses inside the specimen retrofit with CFRP, as this one, could be evaluated. Then I used the fatigue damage accumulation rule to estimate the fatigue life of these specimens. And as you can see here in this figure, in blue, the proposed approach follows the trends of the experimental data in red, whereas other existing methods don't. Now let's move to the fatigue repair using CFRP for crack details. Several experimental works reported the increase of fatigue life of cracked specimens when repaired with CFRP. However, there was no generalized model to predict the fatigue life for design purposes. So I collected experimental data from the literature and I created a database of 152 CCT specimens that you can see here, with and without CFRP. And I derived a parameter beta to be used in the Paris law that you can see here. And this beta will depends on the stiffness of the CFRP, the location of the patch, and also the geometry, and also on the initial damage of the specimen. I used 70% of the data was used for fitting and 30% of the data was used for validation. And as you can see here clearly that the prediction with this model matches fairly well the experimental data. Now let's move to the application of CFRP for seismic design of sea structures. In seismic design, we usually design the building or the structure in order to develop large ductility before the onset of collapse. Basically, the larger deformation capacity, the better performance is. So in steel moment resisting frames, this deformation mainly occurs in this region. So basically, if we subject a frame to a seismic loading, a plastic hinge will form here and large plastic deformations will occur with buckling, with local buckling. In the context of Eurocode 8, some colleagues from University of Napoli, Danielo et al., conducted some experiments on steel beams subject to cyclic loading. And what I found is that the Eurocode estimated the rotations based on the monotonic behavior, but the cyclic rotations are much lower. So I developed a finite element model that can capture this complex behavior of beams, which involves cyclic plasticity and buckling. And I proposed equations for the Eurocode 8 part 3 to estimate the rotation capacities. And these equations were validated with experimental data, as you can see here. One of the important remarks that I found in this study is that the rotation capacity of IPE beams that we use in construction industry are strongly dependent on the web slenderness, as you can see here. So in order to increase the rotation capacity of these beams, I proposed a retrofit solution to extend the rotation capacity, where I applied the CFRP in this, where I proposed to apply the CFRP in this web. So I developed a numerical model that captures the damage in the adhesive layer with the using a cohesive zone model. As you can see here, the bonding. And I analyzed specimens or models with different adhesives. And as you can see here, 2 were ductile adhesives and 1 with rigid adhesives. The models with rigid adhesives showed a poor performance. However, what was important is that with ductile adhesives, an extension of plastic rotation of 10 milliradians could be achieved. This is quite significant if we look at this from the structural analysis, from the global structural analysis perspective. So we can conclude that this retrofit solution has a potential to repair or to increase the rotation capacity of members. So in conclusion, this thesis covered a wide range of subjects related to the application of CFRP to strengthen metallic structures. The potential of this technology was demonstrated for fatigue and seismic problems. Research on the understanding of the behavior of adhesive joint was conducted, and retrofit solutions as well as simplified design procedures have been proposed. In the first part, it was shown that the adhesives used in the construction industry do not provide the best performance for steel structures. And I think this is the main reason for the delay for this of this technology in practice. Ductile, tough adhesives developed for the automotive industry are more suitable. It was also shown that it is important to consider steel yielding as a potential failure mode. And also a new cost-effective high-performance biadhesive joint was proposed. In the second part, it was shown that the fatigue life extension ratio due to the application of CFRP was different at low and high stress levels due to the influence of fatigue loading. So a new approach that considered the influence of fatigue loading on the CFRP patch was developed. And then a fatigue crack growth model to estimate the fatigue life of CFRP repaired metallic specimens was proposed. In the last part, a proposal of empirical equations to estimate rotation capacity of steel members was proposed for the Eurocode 8, and a new retrofit solution using CFRP is proposed to increase rotation capacity of steel members subject to cyclic loading. All these contributions ended up with five papers published in major journals and three to be submitted in the near future, and some conference papers. And for future and ongoing works, I already achieved some works that I couldn't present in this thesis, which are related to the puddle iron specimens taken from Lewis Bridge, and I hope this this research will be carried out by new PhD students. And the preliminary results are that you can see here, where the strength and ductility could be achieved, could be increased significantly by applying this technology of CFRP. And under fatigue loading, the cracked specimen could be improved. The fatigue life of cracked specimen could be improved from 5,000 cycles to 5 million cycles. And for seismic design, ongoing experiment on steel beams with and without CFRP reinforcement is ongoing. So this is the end of my presentation. I would like to thank God for giving me this opportunity, my supervisors and the thesis committee, my family, all colleagues from FIUP, especially from Construct, Mechanical Engineering Department and INEGI. And I'm grateful for the funding of Fiber Bridge. Thank you for your kind attention.
Thank you very much, Anis, for the clear and concise presentation. You can please take off this presentation for now. Yes, okay. So As I said before, we'll start the discussion, the real discussion that is to be started by Professor Carlos Rebelo from the Faculty of Science and Technology of the University of Coimbra. I would like to acknowledge him again for this participation on this committee. So please, Professor Carlos, you can go ahead.
Well, thank you. Good morning again, everybody. And thank you for your invitation to be part of these tools. I would.
Professor Carlos, your words were missed because there was a lack in your internet. There was some words that were lost.
Yes, so I was saying that I would like to thank the Faculty of Engineering for this invitation. I'm very pleased to travel to Porto to meet everybody, but this is the new age of interaction, and so we have to live with it. I would like to address also my compliments to the supervisors, and not only to José, but also to Miguel Castro, who is probably listen us in another channel, and of course to Anis, I would like to wish you all the best for this exam, and all the best for your investigations and for your professional life that you are now, I think you are initiating in Delft. So as the president said in the beginning, so we are now having a lot of colleagues migrating to Delft. You will have here from Coimbra, starting in August, also Professor Traiana Tankova that will join you. Yeah, that's a big loss from our side. That's a big win from from Delft University, and I hope that you will also be happy in that faculty. We have a lot of friends there. Now, coming to your work. So I must say that I didn't like very much to read your thesis, and I will explain why. But I liked very much your presentation. So it's completely the opposite of your written work. Before we talk a bit about that, so I'd like to put you some two basic questions in the very beginning. So I read in your thesis somewhere that you have the motivation. There are two main issues that motivated you to do this work, and one is, and you repeated that here in the presentation, you say that there is an urgent need for the development of retrofitting solutions that are effective and significantly less costly. And of course, we are talking about the steel structures. That's a specific application here, and this is the new of the thing. So that's really your new contribution to this, and I think it's an important contribution that you gave. But my question is, you are always talking about significantly less costly. But did you assess this? So you argue that this is a cost-effective solution, but what is the support for that in your thesis? For this statement? So you didn't compare this with other kind of methodologies or what solutions. Why do you say this? Or why this is your your motivation, but then you don't really show that?
Well, basically, when I said cost effective, I was comparing only between different adhesives, because here I was not comparing with different retrofit solutions. I was only comparing, I was saying that we have to use the ductile adhesive to achieve a high performance, but the ductile adhesive is very expensive. So how can we use it but reduce the cost? So I proposed this geometry where we can use just a little of the adhesive that is expensive, and we can use in the rest the cheap one. So
yeah, so in that sense that you think you have contributed to a significantly less costly solution for the steel retrofitting, so steel structure retrofitting. So then, and that I understand indeed, because you don't have to provide prices for the things, but you showed that in your presentation that it is really an interesting result that you have from your work. So I believe that's I can understand that. But another motivation that you have, and this is basically what you have in your work. So you addressed on one side, so the application on fatigue, another side application on problems of seismic behavior. And you say at a certain time that the post-earthquake reconnaissance, I'm reading your text, so that's why, showed that steel buildings suffered from low cycle fatigue cracks and achieved very low ductility. And this is really true. But you don't explain why this happened. So you put the examples of which usually are put in this when saying this, when referring to these problems of problems with the steel structures after seismic. Before in the past, people thought, okay, steel structures are really very ductile. So if there is for sure there are no problems with steel structures, so we can do what we want more or less. But indeed, it was not like that at a certain point. So people had to recognize that after some earthquakes that it was not like that. But the point here is that, so the main issue in those cases was the one that you want to solve now, or there were other issues, other problems in the steel structures that you probably cannot solve with your technique?
well, in that case, I was just like giving a general idea. I was not talking exactly about the problem, because the problem I know it, which is at welding at the toe, there was like some low cycle fatigue problems in Northridge earthquake, I think. Yeah. So, but I was just like writing and saying like that, like starting like from a general problem that in steel structures we can have this problem and the other problem and another one, and then I treated one of them. So
Yeah, so we will see if you treat it that well or not, and if it is relevant what you have achieved. But okay, so I can understand. So there were problems. Probably there was not exactly the problem that you are highlighting here and trying to solve. But okay, that can be so interesting application of your of this technique, and I can understand that. So this is yeah, that's all about your motivation for this, and yeah, so these two main issues. Now coming to the organization of the text. So it is your text is a bit difficult to read. A bit, I would say, not so small bit. It's a big bit difficult to read. And I believe, and please, if you have another idea, please tell me. But this is basically because you just took the text that you have published in some papers. I didn't check the paper, so but your organization seems that you just take the text that you have in some papers that you published, and for sure important in important journals and so on, but you just take this and you put that in the thesis. So when I read the thesis, my impression is that this is a byproduct of your production of papers. Okay, and I have nothing against that because many people do that, mostly people coming from the mathematics and so on, because it is not that hard to do that in some let's say in some type of knowledge of research. But here you are always repeating some parts. You are always repeating some sentences even, and this is in my opinion, this is not good for the the text that you present. So, but. Please tell me what your idea when organizing your thesis like that.
Well, first of all, I totally agree with you. It is a paper-based PhD thesis. So during my PhD, I was mainly focusing on writing papers. But what I wanted at some point maybe to write a proper thesis, like a traditional one, but my problem is that I covered like different subjects, and it was quite difficult for me to find a flow from the starting point, from the introduction until the end. Because during my research, I was very, let's say, quite excited and curious to learn these adhesives that we didn't study before, and to try to solve different problems because I knew some problems, and so I was trying, and I want to include all of that, and these can't be really like having a flow of one thesis. So that's why I divide in 3 parts, because the first part I had first to understand how this adhesive behaves. And actually, if I continue to work on that one, only on that one, it could be a subject, I mean, of a thesis if I produced more. And it could be like, and it could have a flow, and we can it is like a conventional, let's say, PhD thesis. But in my case, I did like different things, and it was quite difficult to write it.
Yes, so I said at the beginning that I liked very much your presentation, and it's although you didn't use all the time that you were that you could use. I think it was a bit shorter than that usually could be, but you could be completely the opposite of your written work. So it was really, I liked very much your presentation. So you showed what you have done. You showed very pragmatically, objectively what you have achieved and what you are proposing in the new proposals. So because for sure a PhD thesis must have so the new developments, so new proposals for others to even to follow. But exactly in that sense, it's difficult for me if I have a PhD student starting working on this. It's difficult for me to say, okay, please read this thesis, because yeah, I would say, please read these papers instead of reading this thesis. Okay, but but this is important, you know, because at least maybe I'm a bit so aged on this, but it's important because the text that you have in a PhD is something. It's a book. So for me, I have to look at it, the book. So it should have so the normal flow of a book, and not a book of just putting paper after paper. Anyway, even though I have even in that case some criticisms, concerning considering that it was this difficulty, you address different things, but at least I would just propose that chapter 3 and 4 should be just one, because that's, in my opinion, what is so you have in chapter 3 you show some developments, so you find a question how to use these adhesives in steel in a let's say in a cost-effective way. And that's the only thing I would change in this flow of the thesis, of course, concerning this. So you have 3 parts, and for sure it's well. So you addressed well this problem that you had in the beginning. So okay. Now my question is about so in part 3, when you start let's say a new topic in your study, in your thesis, because this is a completely different topic that you did in this flow. You started with chapter 9, where you studied the rotation capacity of existing steel profiles. So this is commercial steel profiles.
Yes.
This is new. So this is new steel. So it's those which are available to be used, to be bought and used in the market. My question is, this was not done by others. So you have references there. So this is not completely, so the question is not completely put in those references that you have. So I saw that you have some references with people that studied this previously in the Faculty of Engineering. This was not completely, let's say, studied by others. So this the problem of the rotation capacity of existing steel profiles. So.
Well, there was one study by a student of Professor Miguel Castro that studied the evaluation of rotation capacity using the same, let's say, procedure that I did, but there was a very important shortcoming, which was that they they studied using numerical analysis, but the way of calibrating the model was, let's say, wrong. And in that way, the rotations are not correct, and we check them.
Mhm.
So the difference between my work and their work is that I calibrated the material behavior, the cyclic plastic behavior properly.
Mhm.
And then I rerun all the analysis with a new model and considering different aspects that they didn't.
Mhm.
So in that way, and then I compared my results with their results and the results of others and also some results of experiments. And my results are much better than theirs.
Mhm. Okay, so that was really a question that I had, because so the time goes by, and I remember to see this type of work, and speaking with also with Miguel Castro some time ago, and seeing the publications, I had the impression that the problem was solved, but apparently not so very well solved. So okay, that's a good reason to include it here, because you have done it, and yeah, for sure. But I have now other questions which are more or less general, and that came to my mind when I was reading the thesis. And one first question is that possible to have preloaded FRP strips, so that when you put them on place, you have some preloading on this, and if that, what do you think about this technique?
Well, for sure we can do that. There are some equipments that are available actually even in the market that we can do that. I think we use a hydraulic jack to do that, and then we put the adhesive and wait until it cures, and then we release. And then that will apply a compressive pressure to the member. But to be honest, in my opinion, it depends on the application, because if we do it for cracked specimens, this will help a lot. But I think in terms of like in practice, this is quite complicated. We can maybe do it in lab. Well, they do it in concrete, but in steel, like you have to clamp the carbon fibers, and then maybe in these clamps you can have some damage on the CFRP. This is quite complicated, but I believe that now there are some ultra high models CFRP that has young models of 650 GPa. I think this will solve the problem without having to pre-stress.
Mm-hmm.
But they have also some limitations, so that we have to consider that.
Mm-hmm. Yeah. So I remember to see that. So these proposals for concrete, indeed. So because in concrete you have really, so you have some advantage of preloading, because you can close some cracks that you may have in the concrete, and this is an added value when applying to concrete. So for sure, for steel, yeah, this can, yeah, being a technique which is probably much more expensive and difficult to apply, yeah, maybe it's not so interesting. But okay, let's keep it open for future PhD students. Another point is that I noticed that all your tests were basically tensile tests. So in all the specimens. So didn't you feel that you should have somehow at a certain point that you should have also 4-point bending tests, or some bending tests that would include the curvature of the the base material, so of the base structure in this process. So what you have is basically you can apply it when you just have tensile forces in your specimen. So the curvature will bring something different to this.
Well, let's say in my test, I was like trying to study the shear behavior of the adhesive joint, and I believe that for sure, if we have some bending, the stress will change completely. But I think if we can model or develop models based on these experiments, we can replicate that numerically when we have a curvature.
Mhm.
It's like it is only the stress state that is changing. So if we manage to develop a model that can capture the damage, the fracture inside the adhesive, which would be the same, but this have to be verified, I mean, experimentally.
Yeah, for sure. No, my basic question or doubt is about so if you have some curvature, so you will have probably more influence of the you have basically two modes. So you may have just shear or you have peeling. So and peeling can become really very decisive, let's say, rupture mode on the thing. So yeah, of course. But of course, if you have models for both, and if you can have some tests, of course you can calibrate the models for sure. Another question that came to my mind when reading. So I don't think you applied this with old base material. So in your presentation, you put that as an ongoing future work, and this is for sure important development, because so I'd say the primary application of the technique is really for all the structures. It can be also more recent structures if you have to strengthen them because of some earthquake or some overloading or something like that. But one primary application, is probably these old bridges like the one that you showed, a very nice one in Porto. What do you think about this? So what will be the difficulties that you will have? So I saw that you have started already to do some developments, but what are basically the big differences or the big questions that are put when using this technique in the old iron, puddle iron or something like that, ancient structures? What do you think?
Well, the puddle iron, well, I already did the test, and usually in puddle iron we have, well, it should be ductile, but it is not ductile because of it has some imperfections, some corrosion. And when I applied the CFRP, we can see that the strength increased and also some ductility. So I think applying CFRP with ductile adhesives there is very promising. But I would say maybe the difference between normal steel and puddle iron will be on the surface treatment, because I noticed that there was like some differences when we were testing normal steel when we polish it, and then when we polish the puddle iron, and then after failure there was some differences. So I see mainly the problem in that sense. But Otherwise, I think it is it works well, or it should work well.
Yeah, so it's basically the difference, yes, in the adhesion and so. Okay, but that's for the future. So these were my general questions. So maybe we could go a bit into some details very quickly through your text that you have. So I put here some questions related to some parts of your text. So do you have access to the text that
Yes,
to your text? So I will refer the page and then we can we can understand what we are talking about. One first question is on end of page 34. It's your number, not the PDF number. So page 34 and then beginning of 35. And this is related to some some results that you get that you got from others, you state that at the more or less at the end of page 34 that the stress ratio of the loading was equal to 0.4. This is always in tension.
Yes.
Yes. So, and my first question is, but usually, so the fatigue is more problematic when you have tension and compression. So when you have R negative, or when you have R negative, what do you think about this? Should you have really, or should you have some other results if you had if you try to do this in tension and compression, or that's irrelevant?
Well, I think it depends. It depends on the actual on the application, which level of compression, which level of tension, if we have buckling or not. This all if we are going to like ductile behavior in low cycle fatigue or not. And well, what I can see from here is that under tension, we have, well, we usually, it's the tension stresses that will open the crack. So if we are putting CFRP under tension, always, it means it will contribute like to reducing the stresses in all cases. However, when we apply tension compression, we might have, but I'm not sure, because CFRP will not have a very high strength strength and also stiffness in the compression, and this might affect the adhesive joint or also the CFRP. But we have to check that. It depends on
another point. Yeah, I'm trying to remember what I thought when I read it, and I have here a note which says that apparently fatigue depends more on maximum load instead of amplitude loading. So it's very dependent on the maximum load that you apply, and not so much on the amplitude of the loading. So is that so? Is this correct?
Well, basically, this is the observations that I found in the literature, and it is widely accepted for adhesives, adhesive joints, that the fatigue was driven by the maximum, because basically, if we if the maximum the maximum amplitude, is quite close to the ultimate stress, or let's say 70%. It is different than when we have 30%. And most of the tests, they show that when we have the amplitude less than 30, we don't have any fatigue damage. That's the reason.
Okay. Good. Now in chapter 3, you have dedicated here, so after page 49, well, some definition of your adhesives.
Yes.
Several of them, but I have here. So you have used not only this, but you have used also Cicadur 370, which is not.
Well, I didn't include it. I talked about it like from other researchers, but it was like just an analogy between ductile and non-ductile.
Mm-hmm. Yes. Yeah. Yeah. So I was wondering why you were using different thicknesses in the steel. So you really wanted to have plasticity in the steel. So then I realized that is that so? It was your objective.
My objective is that I had specimens of puddle iron of 6 millimeter. So I had to test steel with 6 millimeter to see if we have any plasticity, and this occurred, and this changed completely the behavior, completely different.
Yes,
it's quite new. And
this is completely new. Yes, for sure. One interesting thing that you have here also, but that's just a comment in table 3.3 in page 53. You have steel S275 with yield stress of 350. You were surprised about this or not?
Well, because I had some experience on collecting data on steel, so I saw that before. So yeah. I wasn't.
Can you explain that?
Well, because basically I know that the producers of steel have like lower limit to achieve. Let's say if we have S275, they have like a limit like to not be less than that for certain, let's say, thicknesses, but they don't have an upper limit. And that's a problem for seismic design because this will cause overstrength, and this is a problem. So I had some experience with that.
Yeah, I see that you have experience on that. So it's not new thing for you. That's good. Okay. You don't say anywhere what is the width of the specimens. At least I didn't find it, so I tried, because you are always talking about the load. But if you want to calculate the load with the data that you put in, so I needed the width of the.
Yes,
but yes. I didn't find it, so maybe you have it somewhere.
Maybe I have it somewhere, but it's like for all of them is 50. It's 50 millimeters.
50 millimeters.
I will check it and see if. For all of them, 6.
Well, it was my guess at the end. It was my guess on 50. Okay. One point that I did really didn't understand well. You have in your models, in your finite element models, you have clearly you have the steel plate, okay, and then you have the same mesh for the FRP and for the adhesive. So, but you should have basically 3 different regions.
Yes.
It's only the mesh which is the same, or do you mix here something?
No. If you check other, well, when we show the mesh, it is the same. But if we check at the figures, other figures where we don't have the mesh, we can see the difference. Like in figure 313, which is at page 70. It is
Page 70. Yes, I'm there.
Yes, just the figure before. When you see CFRP and adhesive, there is
yes. No. I saw always the 3 layers, but at this point, so okay, what did he do for for the FRP and adhesive? Okay, no problem. So it's understandable. But now coming to figure 3.15, page 72. And we are now, reaching our last 5 minutes. I have just 2 questions. This one is on this figure. So I see that figure C, so the third one, you have maybe in the others you don't see, but you have some strain hardening after the plateau. You have strain hardening. Why do you have this?
Well, this is I think this is the behavior of the steel. I mean, when like in European steel, we have a plateau and then we have harden. This is the case of
and you could reproduce it, because in the others, or at least for sure in the 4th picture, you don't have that. So
because it didn't achieve it.
Sorry,
because the specimen didn't achieve it.
Okay, so didn't reach the okay. Yeah, that's the problem with the different scales. Sometimes is when they are put in the same figure, you tend to look at the scale that you have on the horizontal axis. And I was saying that I had just one more question, and this question is about is on the last chapter on seismic. Which is we can look at figure 10.5 on page 338, and you argue that you want to provide a solution that will not introduce overstrength, but still can introduce some elongation to provide rotation capacity, so to your steel profile. But what I see in these pictures is that you provide overstrength. You provide both. That's what you expect if you put some reinforcement. So if you look at the picture, so you will have some. So you have IPE 400, which is the black curve, the lower black curve, isn't it? And then, for instance, you have the one that provides, for instance, the red one. It provides overstrength and, for sure, so elongation in the plateau, so you have more rotation capacity, but you always provide some more overstrength.
This is in figure 10.5.
10.5, or am I seeing it wrong?
Yes, that's true. But it's the overstrength here is quite limited. So if I applied it like to the flange, it would be much higher.
Yeah, that's for sure. That's not a good idea.
Yes.
But
and
because
that
it seems that so the additional rotation that you have to comply with the code, because you argue that so these profiles do not comply with the American code. Okay, yeah. So indeed, if you put that 80% of MY, yeah, maybe yeah they should be a little more a little bit more ductile. But when looking at this figure, my impression is that, okay, you provide some more rotation capacity, but you also provide some more overstrength. So you still have the problem.
But if we check here the let's say the percentage of overstrength, it's quite not very significant, because it's, I think it's, well, I didn't calculate, but I'm sure it's less than 5%. So I think we cannot really well, my intention was to not add any load, any overstrength, but this is what I could achieve so far.
Okay. No, that's yeah, for sure. If you increase, so the web will have always a contribution, small contribution for sure, because it's very thin, but is always a contribution. So if you have something there, so you will have some more overstrength. The problem is that you do not increase much that overstrength, but you increase significantly the rotation capacity. That's for sure interesting. But I have some doubts of the practical application. It is because this would means that your profiles are not okay. So the people who produce profiles should change them.
We were thinking about that already.
Okay,
we were thinking about that.
Okay, thank you very much. Nice to meet you, and yeah, all the best in Delft.
Thank you very much.
Thank you, Professor Carlos Rebelo. So now we'll move to Professor Nicolas Fantuzzi. I acknowledge again your participation on this jury. Professor Nicolas comes from University of Bologna. Please, you can have your discussion with Anis, please.
Thank you for the introduction, and of course, thank you for the invitation. I'm really happy to be here and to be, let's say, give evaluation about this thesis, the work that Anis did. As a general comment, I would like to say that it's very clear that Anis is a very good researcher, because the amount of work is a lot in terms of papers, in terms of laboratory testing, state-of-the-art review. There's a lot of work here. But I have to agree with Professor Rebelo, because I think that a PhD thesis should be a book. Should be not a book, but at least should be one document. So from one single document, I expect to find, sort of strategy in the beginning. Okay, the motivation of this work is this, state of the art is this, and then you have development, and then you have conclusions. Instead, here you have a lot of state of the arts and a lot of development.
It's true.
And you start one thing, and then at a certain point is slightly change of a topic. Then you go from steel bridges to seismic design, So I was not expecting this, but of course, this is just, some people might see that as a positive. Some people see it as a negative, as a suggestion that I can give you. Because also when I was a PhD student, I really wanted to write a lot of papers. But then during the years, I started to see that we should also be able to present documents for others to read and to understand. And the PhD thesis is something that stays forever, you know, it's forever on you. And when you present your work, it will be, this is my PhD thesis. Okay, people cannot say that you did not work, because actually there's a lot in here, but it is a very complex document, let's say.
Yes, true.
For you that you covered, you know, all the work, it's easy because you spent a lot of time on the work, you know, during these years. But imagine one guy reading the work for the first time. So there's a lot of reading needed, you know, in order to understand and to see what is new, what is from the literature, instead of sometimes if you have an organic document, in the sense that, you know, overall document as a usual document, it's very simple to identify, you know, state of the art and novelty, because they are separate. Instead, here you have several parts and several state of the arts and several, you know, novel things in between. So I find it, as also Professor Rebello said, quite difficult to read. But of course, it's a, let's say, minor negativity, let's say. But of course, not against the scientific achievement, because this is clearly already demonstrated by, you know, publications and the amount of work you did. So this is my general view. Of course, it's my opinion that if I reviewed this thesis, you know, 10 years ago, maybe I would think, oh, this is fantastic, you know. But after some time, you need to find, you know, some moment of your research to make a summary. So doing the thesis is like writing a summary of your work. So I know that it's hard because you covered a lot of topics, but it's also very good for the work itself, you know, to sit down, relax, and try to write something which can include everything and be self-explained. This is also very useful for you to put some points. But luckily, as Professor Rebello said, your presentation was very clear. So for sure you did this job. So for sure you put the points, because your presentation was right to the point, very clear. So you should have, you know, put this in the work, in the text. So if the text had the same structure of the presentation, it would be perfect. It was just, you know, just a collection of stuff, many graphs, many equations are repeated because you just took, you know, from different sources. Sometimes the pictures are a little bit different, you know, but 2 or 3 pictures are exactly the same. You could just, you know, repeat once and just reference to that. But it's you know, this is for next time when you're going to write a book on this. For the book, you have to be very precise. Okay. I have several comments. I'm not sure I have time to cover all this, but I will share with you the PDF that I use for, you know, revising all the comments in. Maybe you can check later, and just in case you can ask. Today, I just want to focus on general discussion because I quite intriguing topic. Also because I was, you know, I'm a civil engineer, so when I started studying composites, I always ask myself, why people from civil engineers do not use composites? Okay, actually they use concrete, but not real composites from automotive. So I have a lot of questions right now about that. Then I have, as Professor Ribeiro said, also some points from the PDF. So just point to the page and then we discuss. So I want to start with this. Right now, we live in a world in which every day you turn on TV or you just check project call from European Union and talk about sustainability. Okay. So clearly your work goes towards sustainability in the sense that you want to preserve the structure in place. We can agree and disagree on the phrase you put in the presentation that you don't change the architecture of the structure. Because I don't know in Portugal, but believe me, in Italy, if you put a strip of FRP outside of a building, they say no, because the building has to be exactly as it is. So not sure if you put a strip on a bridge, which is historical, you can do it. But in any case, the problem of sustainability is quite challenging. And I'm just wondering why you didn't mention it. I mean, I would expect from this kind of topic a stronger mention in the thesis. Why sustainability is important? Because especially for steel bridges, I was thinking, okay, I want to restore steel bridges, right? But okay, if the bridge is historical, like Luis Primeiro, I agree. I have to keep the bridge exactly where it is in the same shape as it is. But for any steel bridge, and there are so many steel bridges in the world,
Yes, sure.
why I should keep those? I mean, is it sustainable to retrofit those? Because for sure, if I just destroy it and reuse the steel, I can make a new bridge, right?
That's true.
If I put carbon fiber on a bridge, then can I still recycle it?
Well, it depends. Well, it depends on the problem. But in my case, I'm looking at fatigue in local details. Like, for example, you can have a bridge with a deck that have a crack only in one part. How to solve that without we can solve it by using very small amount of FRP, and we can stop that crack. How to stop it? So I think in that sense, if we use just little amount of FRP, we can later on to recycle it. But if large amounts of FRP are needed, maybe not, or I don't know.
There was a colleague saying that if you want to stop a crack, you just need to drill a hole.
Yes, I did that. I did that actually, and in some of the specimens of puddle iron that I showed, and actually in that work that I couldn't include in this thesis, where I did cracked specimens, and then cracked specimens with a hole, and then cracked specimens with the CFRP, then others cracked specimens with a hole and CFRP. And usually the FRP, like when we use the FRP, it works well. I mean, it increases the fatigue a lot.
Okay. So let's stay on retrofitting. So clearly, putting FRP, CFRP improves the structural strength of the structure. But I wonder, I don't know if you thought about this. What is one of the main issues of reinforced concrete bridges or structures in general? That you cannot see what's happening to the reinforcing bars, right? So I'm just wondering, if you put these sheets of FRP on top of steel, can you still check the health of the steel below it? Because if you cover a crack, then you put this maybe on two sides, you know, can you still check if the crack is propagating or not?
Well, visually you can't. And I was thinking about that actually. And well, I thought about it. And well, it depends really on the situation. But let's say if we have a large girder and we have a crack near the weld, and we are going to put small strip, we're gonna see it if it grows, because it will go beyond the strip. But let's say if we have a small part, and during my test, and actually I was going to do it, and I started to do it, but hopefully my supervisor stopped me, and they said, okay, Anis, you have to stop, because during my test, I was checking, I was learning a lot from our colleagues in the mechanical engineering department, where they use some CFRP with some steel plates. It's like, it's called, I don't remember, but it's like a steel laminated FRP. And
yeah,
actually,
some people call it glare if you have aluminum for aerospace.
Yeah,
there's a lot of applications, steel and composites.
And actually, I made one specimen, only one specimen with that, and in that specimen, it was complete. Well, the behavior was completely different, because there was no a brittle failure. The peeling started in the end of the joint, and the steel yielded, and you can see it clearly, and it was very slow. So I was thinking to develop, or not to develop, but to propose this solution as a warning, that if we have the crack that is increasing, it means that the CFRP is failing, right? Because like it will have a large displacement. So in that sense, the steel part, or the FRP, you can see that yielding clearly, the peeling, you can see it. I have some pictures. It's very interesting. I was actually planning to do it, but hopefully they stopped me. So in that sense, I think that is one of the solutions, to know that there is something wrong in this intervention.
You know, now I remember, it's fiber metal laminates.
Yes.
Yeah, it's used a lot in automotive. Okay. So I'm still referring to the first slide. The main point was to retrofit bridges, right? So I was expecting, at least, I don't know if you thought about it, but maybe you didn't have the time to do the test, or you didn't have chance to make any kind of test about corrosion and the effect of environmental impact on the composite, because the environmental impact on steel, we know since 200 years, more or less. Maybe not 200, 150. Huh? But we don't know what is going to happen if I reinforce the structure and then how this carbon fiber stay there. Because in this case, we cannot use automotive and aerospace as a reference. Why? Because the life of their component is very short.
It's very short, yes.
Very short. For automotive, very, very short. For aerospace, okay, not so short, but not as ours, 50 years, 100 years. Some bridges are there, you show some pictures, 1880. Huh?
Yes, yes.
So many years. Okay, yes, there was some, for sure. People did, some work on that. But we know steel very, very well. We can say that. We cannot say the same about composites. What is your opinion about this?
My opinion is that, well, it is true. I agree with you. But let's say if we have a crack and we are going to, well, it means in that bridge we are going to have, and we do an intervention and repair it. But I don't believe that we're going to repair it forever. I mean, it will have, let's say, we extend the life, let's say, okay, for 5 years, for 10 years, and maybe later on will be another solution, or it will be at least monitored.
Okay. So at the end of this, we should maybe cut and replace the part. I don't know, after a lot of repairs.
If it is possible, yes.
If it is not a main component,
yeah.
we hope. We hope it is not. Okay. All right. So I up a little bit because there are some things that I really want to ask you. I read in many sections of the thesis. I read, data from references, data from here, data from there. As you know very well, I'm sure, the data-driven model are, you can find it in every corner. Yeah? You open Google and you find that data-driven, models. Did you think about, apply any kind of, maybe not 100% data-driven, because I don't believe in that actually, some physics-informed data-driven, which is more, I think, accurate for our interests, for crack growing models, since you had so many information from the literature. Did you think about that, or do you think you can do this in the future? Do you think it's interesting to do it in the future?
Do you mean go in deeply understanding how the crack grows?
No, because you present your own methodology, right? In this work, based from you said from the study in the past and trying to fit better the results. But do you think can you be more specific or more general? Because maybe the literature is not 100% covered, and maybe future, applications are not covered. Is it interesting, in your opinion, to set up a sort of AI, artificial intelligence, to predict the crack growth?
I think
in materials in general, in steel or composites, steel plus something else.
I think the crack growth, the methods that at least I'm using here are empirical, based on experimental data. So for sure we can do the same with with AI, but to be honest, I don't have any experience with AI. But I think, well, I know that it is a matter of fitting, and like, yeah, so if it is a fitting, so for sure we can do something with that.
Very good, very good. Okay, so let me. We'll do the same. I'll tell you the page and then we discuss. Huh? Let me find the page. Okay. Page 38. So in page 38, you wrote a quite intriguing phrase. Like, according to Agani, or Agani, I don't know the pronunciation, stress singularities in adhesive joints occur at geometrical and material discontinuities. Okay, I agree very much with Agani, but singularities appears always in geometrical and material discontinuities, not only in adhesive joints. Okay. So in general, this is something, you know, people from finite elements,
Yes,
in the origins, in the 60s, you know, discovered it. There's a very, very good book about finite element, you know, from Gilbert Strang, you know, one of the guys from MIT. There's a chapter which is called Singularities. And it's a book about finite element, mathematical formulation of finite element. So maybe Agani for sure did a great job, but in this context, you should have cited, you know,
something else.
maybe more, yes, no, just, you know, more specific on numerical analysis, because this is a general aspect of numerical analysis. Okay, and also just one page below, figure 2.17. I know that this is taken from Agani because it's a reference, right? And this shows the clear, you know, effect that if you put a very fine mesh, the stress goes to infinite, right? But I think there's something wrong here, because one curve is doing like this. You know, it's not smooth, it's oscillating, you see? It's the curve with 0.0125. So I think, and also some others, you know, are doing like this. So I'm not sure what kind of simulation he did, but there's something wrong with the element. This is called hourglass effect. So I think this analysis has something wrong in terms of finite element used. Okay.
Honestly, I don't really remember what he did. I read what he did, and it was published in a good journal. And actually, these researchers are quite. I mean, produce quite good quality research. But I don't remember exactly what they did. But maybe, well, I had this when I was doing contact. When I model contact, usually I have this, and maybe they put some contact between the adhesive joint and the steel, but I'm not sure.
Yeah, but you know very well because you use it. If you use Abacus, most of the finite elements, when you do the model, they say hourglass control. So maybe, you know, they deactivated it, or they just use an element without hourglass control. So this thing happens quite easily. If you just unclick hourglass and run the simulation for some kind of application, you will see this in Abacus also. So it's a numerical, you know, numerical detail. Okay, go down. I will be quick. Okay. Page 53. Table 3.3.
Table 3.3, yes.
You should explain to me why the yield stress and the ultimate stress is different.
Because it's two different bars.
Yeah, but the material is the same.
Yeah, but you will never have the same monotonic behavior. Even in the same bar, you will have some differences. This is hot rolled steel, and with my experience on at least analyzing the data, we have high variability at the yield, at the actual yield stress.
Because I remember from I'm quite I cannot say an expert, but at least I read some references about design of offshore structures, because this is what I teach, you know. And in some regulations, there's a clear reference about thickness, but the reference thickness is 4 centimeters, 40 millimeters. So there's a difference, there's a change in mechanical properties if the thickness is more than 40 millimeters. Here I saw 6 and 10. So for me, in the dress of a designer, for me, the S275 is the S275. That's it. The mechanical properties are that. I don't have to test it again. And if I test it, I should get within a certain level, more or less the same result. Here we are talking about 350 and 324.
Yes. Well, the 275 is the minimum. And when you test the monotonic, you will see that you will have always much more, always much more. And there is a problem. This is a problem actually, because I don't know if you are if you are aware of seismic design, but usually in seismic design we don't want to have a higher strength in the ductile member. Let's say if we want the beam to dissipate energy, we want to make sure that the beam is weaker than the column.
Yes, indeed.
And we have to take into account this overstrength, this problem, because this is quite a problem. Because I know people from seismic design were asking people from metallurgy, can you make an upper limit? Because we want to use a factor to make sure that our strength is always lower than the column. But when they couldn't, and we have always higher, much higher.
Okay. All right. So in the page below, you are discussing about how you prepare the surface, for the application of the composite. So once again, I was, here they're using this blasting machine, sandblasting machine. But how can I do this in a location, in place, in situ? I go.
Well,
what I'm gonna do?
Well, there are some equipments that I know that sometimes to apply some corrosion resistant paint, they use this, and this is applied. But I think this is not a very big problem, because in some of the tests that I conducted, there is quite new adhesive that is RLD 2052, and they claim that we don't need much of surface treatment, and I checked that, and it works, and we achieved very high strength without using this let's say, intensive surface treatment. And I think if someone's used this new type of adhesives, we don't have to go to do that.
Also because I think sandblasting, I mean, in the machine is okay, but in situ is not sustainable, you know. Yeah. Just throwing, I don't know how much material in the environment without recovering.
But they but now there are some equipments that they throw in the same time they suck the particles.
Very interesting. Okay. Let's go. Let's go fast. Okay, this is just my curiosity because I've recently studied some the mechanics of delatency, you know, the delatency effect. So this is, I'm not sure this is happening, but when you have steel, you know, and you put adhesive, is the surface always completely, really smooth? Or do you have any sort of delatency? You know, delatency happens when you have rough surfaces, you know, like, you know, in cracks of concrete, for example, that when you have a crack in a concrete, sometimes people say, okay, the crack is, you know, void. Actually, it is not, because the two surfaces of the concrete, they have friction, and sometimes they have this delatency, and delatency can generate, you know, extra pressures or more opening, let's say. So I don't know if you noticed in your experiments or in the literature you found any paper or study regarding the latency effect on this.
To be honest, I have no knowledge about the latency, but what I can tell you is that these surfaces are quite rough, and we have to do that to apply the adhesive to have mechanical interlocking. So this is the main, let's say, the main phenomenon that will help for like having higher strength and higher bonding. But for other problems, I'm not sure. I didn't check anything.
Okay, thank you. Okay, now we go to a very important question. I put very important, so it must be very important. Let me see. Okay. Okay, sorry, page 107. One part of the question is very simple. Maybe it's just a typo, because you wrote that all the model was developed using plane stress, linear, quadrilateral, blah, blah, blah. But is it the real plane stress? I think it should be plane strain, because you are cutting, you know, and so that you have, you know, infinite, it's not an infinite, it's very long structure within a cross section. Doesn't change much. I mean, the results are slightly different because there's a difference in terms of Poisson ratio between plane stress and plane strain. But I think the best finite element for these applications are the plane strain finite element, not the plane stress, because plane stress are flat, act with forces acting on the surface. Plane strain is opposite. You know, you act, but it's like having an infinite structure.
Understand that. Well, I did some with plane strain and plane stress and checked that. And actually the difference was not significant. And I actually went for this because these ones took less time to analyze. This is the main reason.
Very strange. You should take the same time.
Yeah, but it wasn't, because we have very small mesh, and we have some plasticity, and it was not taking the same time. At least some, if I remember well, some problems of convergence.
Okay, I have no idea about plasticity.
Yes.
But between plane stress and plane strain, the only difference is the constitutive matrix is the same element. It should be the same element. And I think also in plasticity, very strange. I mean, the difference is that one problem has 0 sigma normal, sigma, if you have, I think you used X and Y. Yes. You have in figure 416, page 110, you have X and Y. So if that is a plane stress, sigma ZZ, which is out of the paper, is 0, which is actually not true, because this thing has stress in that direction. So this is plane strain. What it doesn't have is strain out of the plane. But as you said, it is a minor difference. It is a minor if you're not reading the stress. Because the sigma Z is not important in this problem. If it is, you will see the difference.
Sure.
Because one is 0 and the other one is different from 0. So not the same. Okay, the other thing is, which you did not convince me, is page 107 at the end. That you used isotropic because instead of orthotropic, but the material is orthotropic. So why you used isotropic?
Well, because basically
Sorry, you used isotropic, but which properties?
I used the tensile ones, and yes, and I know that it is orthotropic, but in very similar test, there was one work that used both and showed that it has a minor effect. And my problem is that how to define these properties. It was a bit of headaches, like because we had to test, and the test was not easy, and then I dropped it and used these ones.
Okay, generally, okay. I think that the results were good enough because the CFRP is very thin. I think you were saved by that. Yes, 5 minutes. I will finish. I have so many others. You will check later. It was so thin, So that means that if it is thin, it is very rigid. So the effect in that direction is 0.
Okay.
So you were safe, saved by this. But believe me, if you do a block,
Sure.
If the steel bar was the CFRP, for sure not.
Yes, for sure.
And I think I found it written somewhere, or maybe I was just confusing, but in composites, if you don't want to make a lot of tests, what you do? You do tensile, as you did. So tensile is E1. Then E2 and the others are just the elastic modulus of the matrix.
Yeah.
Because transversely to the fiber, there's no fiber, so there's only matrix. The matrix is the main stiffness direction.
Yes, but even tensile is not easy, because we started to do some tests and we were having some problems in the clamping. It's like there was something, because I tried to do that, but I had very limited time, and I had these problems, so I couldn't really spend a lot of time to make other specimens so.
When you have limited time, the best you can do is to use rule of mixture from homogenization theory.
Yes.
One equation, 2 minutes, you get properties.
Yes. And actually, I think I used it somewhere. I used it.
Yes. 1 minute. Let me just ask this question. Because we talked about it with Professor Rebelo before at page 329. It's not clear to me why you put the CFRP in the web.
Yeah.
And why you put it in that way. Because the web is subjected to shear mainly.
Well,
so at least you could put it in the other direction.
Well,
right?
Well, it's not subjected to shear. Well, it is when we design it, but when it is subject to cyclic loading, you have compression in all the upper part, and you have tension in the other in the lower part. And the problem is that when you have compression, part of the web is under compression in that sense, and this will cause buckling. And buckling in the web is the main cause for loss of strength and limiting the rotation capacity. So my point is, when I put the strips in that direction, it will, well, first help to reduce the accumulation of plastic strain under tension. And also, when we have buckling, it will counteract these bending stresses by the buckling. So it will try to keep it stable.
Yeah, but I don't know, maybe further developments must be done on this part, because this was just, because also this kind of buckling, local buckling, if we see that as local buckling, I'm not sure it's buckling, because after plasticity, who knows what's happening?
Yes.
If it is just plastic regime, it's not buckling. But anyway, I'm expecting, when I design a steel resisting frame, to have close to the edges of the beam, I have reinforcement, in the sense that I put vertical, plates to create a rectangular, let's say, cross section to be more stiff. So also I try to increase the plastic area close to that area, right? So I'm not sure this kind of CFRP is beneficial for.
Well, basically, we can put some steel plates at the connection level, but beyond we are not allowed. And this has a reason, because if you put a steel plate in the plastic hinge region, this might generate some low cycle fatigue problems. And this is called, let's say in the American code, it's called the protected zone, because they had a lot of problems with low cycle fatigue, and they don't want any welding in that region. So this is why I use this.
Okay, very good. Thank you very much. I finish my discussion. Thank you.
Thank you, Professor Nicholas. So we are now moving to Professor Abílio Jesus for making your discussion, please.
Yeah, good morning, everyone. I'd like to start greeting all colleagues from this PhD jury. I want to acknowledge the invitation for this jury as well. And I want to wish also the best luck for Anis Mohabeddine for his future career and personal also life. Regarding the research topic, I have to say that this is really a very hot topic. I have listened all the discussion, and it seems that we are in the beginning of this field when we talk about civil engineering, well, metallic structures. So it seems that we must learn a lot from mechanical engineering applications and try to transfer the existing knowledge to these large structures. Of course, the challenges are present, very big challenges due to the scale of the structures. So we need to look for this kind of multi-scale approach. So I was very pleased to read the thesis, the concerns about the interface, the local geometry of the bonded joints, and afterwards we want to apply this to the large scale, which actually was not totally explored in this PhD research. I believe this is a good starting point for the future. Regarding the overall analysis of the thesis, I shared the same opinion of my previous two colleagues regarding the extension of the work. However, it reveals to me how hard worker is Anis. So I was in the previous PTI discussion, the seminar for the PhD of Anis, and I was very surprised when I read the thesis, because I found a lot of novelties. It is supposed, but the amount of novelties was really surprising. Regarding the reading, how it could be easy or not, well, I have to say it is not easy to read this very long document, and the reasons were already mentioned. So the thesis was designed for self-independent chapters, which has some drawbacks, as we could understand. But thanks to that, we also are pleased to see that some papers have been already published. Maybe I would recommend a final revision of the document, where some points should be polished. For example, due to these self-independent chapters, there is some inconsistency in the nomenclature, or, for example, very basic example, the equation numbers are repeated along the thesis. So this is something that you, Anis, could amend in the final document for sure. And the final global comment I want to say is about the two main topics of the thesis. This was already referred that maybe, I'm sure that just one of them would be enough for a PhD research. I understand that you have Anis two supervisors with major in fatigue and seismic analysis. So I understand that your final thesis is a result of this marriage between the two main topics. Maybe my first question is about the possible interaction that could be between these two topics. So, for example, I can guide the question to the numerical features or numerical modeling. So, in both fatigue and the seismic or cyclic analysis of the reinforced components, you have used numerical modeling, and I realized that in the case of the fatigue analysis, you did not explore the cohesive damage models, cohesive zone damage models, but you did that in the seismic or cyclic analysis of the beams reinforced with CFRPs. Why did you not profit from that knowledge, that models also in fatigue analysis? So this is my first question for you.
Well, I have one conference paper where I used local approach for specimens with puddle iron with and without CFRP, and I used that. But due to time limitations, I couldn't include it in this because I had to improve that paper to include as a chapter. So, and I couldn't really put it here, but I used that. I mean,
Yeah. Yes, I understood. And I was very surprised because you did the most, I would say, challenging part, that was to run simultaneously cohesive zone damage models with plasticity, which is usually raises some convergence issues. So you did that properly in the final part of your thesis. And when we talk about fatigue and the kind of applications you are deal with, I don't expect too much plasticity. So maybe it was easier to use cohesive damage models in that field.
Yes, that's true. I mean, it is much more easier because for those beams, like the beams are quite large. So if we reduce the mesh too much, it will take very long time. And then I had to do explicit analysis, and to do explicit analysis, I had to, if I reduce the mesh a lot, it will make it longer a lot. So I had to really search how to find like solution to implement it. And hopefully I found a work by, I think it was Professor Kamani, I think, yeah. where I think it was with NASA, but they provided a solution how to use a coarser mesh while we have still a valid cohesive zone model. So I implemented that, and hopefully it worked. So
okay, just since we are talking about well, I have started from the end, so maybe I have one question about the last part of your thesis and about modeling. So you applied a mixed failure mode, right, for the cohesive zone models. But well, my question is maybe related also with the Nicolas Fantuzzi question about the loading mode of the patch. And I was expecting some concern about the mode 3. I was expecting some kind of mode 3 loading in your patch when you put in the web of your beam. I'm not sure if I'm seeing well the deformation modes, but I was expecting in your cohesive damage modeling some mode 3 mixicity.
That's a very important issue that I didn't include, but I think it should be included. I mean, it might have some effects.
Yeah, because it seems that you had a very premature failure of the patches. Maybe that could be the reason you just neglected an important part of the fracture energy of the patch.
Yes, yes.
Okay. I have a very small time for my discussion, so I would say that, well, I have here one comment about the application of your numerical models in your thesis. You said, you have said at least a few times, 2 times at least, that you are using numerical models to validate experimental work. Can you comment about this? Maybe I can understand your idea, but it seems the way around we are used to do. But okay, please comment on that.
Well, basically, for sure, experimental data are like the physical test. Is the reality. But however, if I have a test and how and everything is well, but how can I be sure that I didn't have something wrong, maybe? So when I cross-validate with numerical analysis and they see that it is somewhere the same and somehow the same, so it means that it is okay, and I didn't have any big issue at least. So this is why I was always like trying to, like, if I do numerical, I have to validate with experimental for sure. But also when I do experimental, I want always to do some numerical analysis to make sure that it is consistent at least.
Yeah. Yes, I understand that perspective. We need to use also numerical modeling to design a proper experiment, right? But afterwards, we want the experimental data to validate our modeling predictions as well. So it's a kind of we need to go back and forward just to have a good model and good experimental data as well. I have here a very old question because I remind myself that I did that question in your PTI. It's about the way you model your tensile tests with the reinforcements. So it is very interesting because, or I'm wondering why you waste a lot of resources, computational resources on the gripping system. Did you felt some sleeping on the gripping? Why you are modeling gripping with the contact elements when if the gripping is properly designed, we just put some displacement on the volume or on the end faces of the specimen, and everything should be okay.
Well, basically, I was checking the specimens one by one if I had any sleeping, and I didn't see any. But since I had some plasticity, some very ductile behavior, and that's very, I didn't see it in the literature at all. So I was saying maybe I have a problem. So I tried to model the compression by the grips and see if I have next to the grips any concentrated zone of plasticity or anything, but actually it wasn't. It was the steel bar that was yielding. So it was just a confirmation for me that everything was okay.
Okay. Another comment slash question. I have to congratulate you again because you did a very tough work, very long work also, and you have to fight with experimental data. So because you did not get your own experimental data, as I expect, that was your original idea. So, but anyway, you were very, you solved the problem using literature data, and that is excellent. And I found that you discover the proper data for demonstrating your techniques, your modeling approaches. And another point that I found that you actually you use the numerical simulation just to confirm the stress fields, the strain fields that you are looking for, the boundary conditions of your experimental setup, if they are properly designed, and then you went to the analytical equations. And that is a very good perspective because you talk about in your thesis many times about the design procedures, and the designers usually prefer design by formula than design by analysis, and you went in that direction, and that seems a good option. My question is about what can you comment about the generality? Or could you generalize your findings regarding, for example, the effect of the CFRP patches on non-correct specimens or defects of the patches on the CT or not CT, the correct specimens. I see that you did a very interesting approach, analytical approach, but now I would like to hear you about the possibility of those approaches could be generalized and applied and made available in design codes.
Well, problem in, well, let's say in the analytical model that the empirical analytical model that I provide for fatigue crack growth, well, I didn't find any like reliable model to use. It was mainly because I wanted to design my experiments on puddle iron. So I had to understand what's really going on. So I collect all this data, and then, well, all the data that I could find, and I derived this model, and this model seems to work well, and also the experiment worked well. But I think to generalize it, it has to be more validated, and also maybe applying some statistical analysis. So to use some reliability analysis to make sure that we are always in the safe side.
Yeah, I think your thesis it will be a very good asset for the future because it opens a lot of topics for research, and some of them still have interesting ideas that we could explore afterwards about that, and maybe try to make some cross links between chapters. That was you were saying. So you have one chapter about statistical and probabilistic modeling. We have another about reinforcement. Why not make the connection between both? Regarding, maybe I am just, I was informed that I am almost achieving my limit time, but maybe I have one or two questions just to close my participation. But the other, well, the question is about your the analysis you did on the reinforced or repaired cracked specimens. So you did a kind of regression analysis, and for that I agree with Nicholas that could be artificial intelligence possibility, but I am also in favor of the physics, or mostly in favor of physics of the problem. And what about numerical analysis? I think it is a very, I would say, not complex activity to get some results, because it's a question of the cracking driving force. If you could evaluate numerically the cracking driving force, for sure, you will be possible to apply in any application. Okay, can you comment on this?
Well, it was in my plan to do some numerical analysis on that, but I was mainly planning to do it after the experiment of puddle iron, and I couldn't have enough time to do it. But for sure, with the validated numerical analysis, we can generate more data, and we can have more insight on the behavior, and we can have some more reliable models. But there are also some issues on if the CFRP or the adhesive is going to be affected by the fatigue loading. So if we have to include that, it is an open issue. It's not only the steel, but always we can do something about that. I mean, for sure.
Okay, my last question is about, well, you talk about, again, going back to the design. I am the only mechanical engineer in this jury, but I am trying to focus the final output of the thesis for the designers. But in your opinion, what is needed just to allow that we could provide to the technical committees regarding zero code developments. So what, in your opinion, how could your work contribute to that standards? So I'm talking about fatigue, okay? So in the future, I want to see some design recommendations in the Euro codes, and in your opinion, how far we are from that?
To be honest, well, this was kind of like my main goal, to understand and how to contribute in that sense. And after testing static and some fatigue and all these works, I think the problem with CFRP and adhesively bonded technology is that we have different behaviors if we use different CFRPs or different adhesives, and also the adhesives are very important. But let's say, to simplify, I would go for, if we can prove experimentally that, let's say for crack propagation, if we can prove that experimentally with this type of retrofitting, let's say this type of CFRP and this type of adhesive, we have a crack arrest, for example, we can use it, which will be more reliable. Because I think if we are going for a little bit of improvement, let's say a ratio of 2 or 3, so the designer will have always to do a lot of calculations, and which is quite complicated. So I would go for like in a way that we provide retrofit solution, like certified patches that we can use without having to go through difficult analysis, and this will be done experimentally and by researchers.
Okay, Anis, thank you very much for your replies, and I wish again good luck for you. And from my side, that's it. Thank you.
Thank you, Professor Abílio. Now I will give the word to Dr. José Correia on behalf of the supervising team. So you can close at least with this part of the discussion, please.
Okay. Thank you, Professor Rui Faria. I would like to say a lot about the work and about Anis Mohabeddine, but it's not possible. We don't have time, and we need to comply with the rules. So I want to start my intervention by thanking the jury members for their comments and the suggestions during the discussion with Anis Mohabeddine. That is also important in this kind of public defense. I want to thank Professor José Mila Castro, co-supervisor of this research work, for the fruitful discussions that become relevant and extremely important for this research. Additionally, the work that was developed by Anis was part of the Fiber Bridge project funded by FCT. Okay. Regarding Anis Mohabeddine's performance, I would like to say that he showed a high level of autonomy in the development of all tasks. Anis Mohabeddine is a person of excellent personal and professional qualities. You demonstrate great responsibility, maturity, independence, objectivity, and also organization. Finally, I wish you the most sincere personal success and all the best in your new position as a researcher at TU Delft. Okay, thank you. Please, Professor Rui Faria, from my side, it is all. You can take the word.
Thank you, Dr. José Correia. So, the jury, this part of the the discussion is closed. So the jury will meet on a private room. So I ask Anis to wait on a waiting room until we reach the final decision. Then we call you just to provide you the final decision of the jury. Okay?
Yeah.
So I asked Miguel